This video is an example of motion on a ramp. Here's the problem that we're going to be looking at in this example. In the summer, a block of ice can make a nice sled on a grassy hill. If the hill is 20 meters tall, has a slope of 25 degrees above the horizontal, and the ice block with you on it slides with no friction, how fast will you be going at the bottom of the hill? Whenever we get a physics problem, we want to take a moment, take the time, and make sure that we really understand the question. The question is, what is the final speed? How fast will you be going on a hill with an angle of 25 degrees above the horizontal, 20 meters tall, if there's no friction? Now, the how fast, it's a little bit ambiguous if we're looking for speed or velocity here. I'll probably end up solving for the speed, and then I can go ahead and indicate that the sled is sliding downhill, and that'll be a complete velocity. That covers the bases. I'm going to start by organizing my thinking about the problem with a drawing and sort of organizing the variables. So I've already gone ahead and made a little ramp here. I've put a block on it. We can pretend that's the block of ice. We can go ahead and put a person on here. I'm going to make it a little person to save room. I guess that's a huge block of ice. The problem tells us that the hill is 20 meters tall, and that this angle, the angle of the slope, is 25 degrees. So what we're looking for is a V final. That's a final. I don't know what that is. To solve this, I usually need to know something about the initial speed. You know, the problem doesn't say, but if it doesn't say, it's usually safe to assume that we're starting at 0 meters per second. Here I have a distance, but that's not the distance that the block actually travels. The block is actually going to travel down the hill this way. So I've run into my first kind of snag with this problem. I need to set up a coordinate system. Since all the motion is along the surface of this ramp, I'm going to go ahead and set up my coordinate system tilted to match the ramp. And so moving down the ramp is going to be moving in a positive x direction. So this is going to give me a delta x, which is actually the hypotenuse of this triangle rather than the height. So I'm going to make a note that my delta x, my change in position, is going to be the hypotenuse of the triangle. Let's see, I know this angle, 25 degrees, and I know this side, 20 meters, which is the opposite side. I'm going to use sine to calculate this. If sine is equal to opposite over hypotenuse, then to solve for the hypotenuse, I'm going to need to take 20 meters and divide by the sine of 25 degrees. And so when I solve that, I get 47.3 meters. I've put in an extra sig fig here, but since this is an intermediate step, that's actually good practice. I can always round off my final answer to the 2 sig figs that have shown up in the rest of the problem. So I know my delta x, I know my v initial. The other thing I need to find is my acceleration. So in these problems, well, we know what's pulling the block down is the acceleration of gravity, which points straight down at a 9.8 meters per second squared. But I need to find out the component that matches my coordinate system. So I need this a sub x, which is this component of the triangle. To do that, I'm going to use what I know about the angles. This angle right down here is my 25 degrees. And so to solve for a of x, that's going to be 9.8 meters per second squared times, and I'm running out of room on my little screen, times the sine of 25 degrees. And so this is going to work out to an acceleration of 4.14 meters per second squared. Alright, I think that's about all that I know. I know a v initial, I know an acceleration, I have a delta x. So it's time to decide what kinematics equation I'm going to use to solve this problem. The kinematics equation that I think I'm going to end up using is the one that gives v final, vx final squared equals vx initial squared plus 2a sub x times the displacement delta x. So let's take a look at how that works out next. Alright, here's the equation that I've selected. Vxf is the final speed at the bottom of the hill. I don't know that. That's what I'm trying to solve for. I assumed that the initial speed was 0, and my units here are meters per second. I can write a squared because that should be squared, but it's of course just going to turn out to be 0. Plus 2 times, and the acceleration worked out to be 4.14 meters per second squared. Now the coordinate system I set up made that a positive. That's a positive 4.14 meters per second squared, which is a little bit counterintuitive, but I chose a coordinate system that made downhill positive x direction. And then the distance that it travels is 47.3 meters. So I'm going to take a simplification step. We're going to drop off this 0 part. That just goes off to 0. And 2 times 4.14 times 47.3 works out to 391. And the units at this point are meters squared per second squared. To get just Vx of f, I have to take the square root of that. And my final results is I get 19.8 meters per second, but if I'm being careful about my sig figs, that rounds off to a 20 meters per second because I round up 20 meters per second. That's pretty fast. I recognize that number. That comes up in a lot of traffic examples. That's car speed, but you know what? That's not totally unreasonable to actually hit those relatively high speeds sledding. In fact, sledding can actually be very dangerous. So I think we've solved this problem.